Before we get started, just a reminder of the YouTube channel. You'll see there are 3 different playlists. One is my Deep Thinkers, one is what I call my Mathcad Bites, and you can see the full playlist for that. These are short videos explaining some of the calculations in Mathcad, and quite sneakily I've taken these out of the bigger longer seminars. So most of these are about 10 minutes or less, and worth a look if you just want the calculations. And the full playlist for the CPD webinars, here we are going from CPD webinar number 2 all the way through to number 19. So welcome to another CPD seminar for structural engineers. This is number 20, and congratulations if you've attended all 20 seminars. In fact, this is part 5 of the series of 5 on structural insulated panels, and a double bonus if you've been to all of them. And so today we're going to look at load span tables for a composite panel to be used in a warm roof. So there's no spreadsheet for this. We'll be just using Mathcad to derive the transform section properties of a composite panel from first principles. Then we'll use matrix mathematics to derive the load span tables and the graphs. So a reminder of the whole SIPS series. We started with tiny houses and modular buildings. We looked at how we calculate the structural capacity of panels. Then some case studies on cold stores and freezers, some detailed calculations on the capacity of fixings in steel and aluminium, and finally, for the end of the year, we're looking at the load span tables. So we're looking at transform section properties and how we build up the load span tables using Mathcad matrices. So because we're using matrices, I couldn't resist it. By the end of today, you'll just be seeing lots of columns of numbers, and today is the big one. This is going to be quite a long session because there's a lot of calculations to look at. Feel free to pull out when your head is about to explode. So we'll be offering you a choice, and we have Mathcad and we have Excel, and we'll be delving into a little bit of both. And just a reminder, just because I'm showing you all these calculations in Mathcad doesn't mean I do all my calculations in Mathcad. I use the most appropriate tool for the job. One of the advantages of Mathcad is that it allows you to explain in detail the calculations long form. You're using Excel and you can hide a lot of the information in Excel, and that's why it makes it very difficult to check. By all means, use Excel when you're confident that the Excel sheet is doing what you think it's doing. If somebody else has written it, you should be asking, where is the validation for this Excel sheet? So we'll start with some Excel. We start with how we calculate the capacity of the roofing sheets itself. So let's open the Excel. Now, Metalcraft took on board the requirements for testing, and they did a whole series of tests on different roof sheets. So Metcom, Kahoo, MC965, and so on. So we delve into a single table. Here are the SLS loads for the 4 different variations of Metcom. So it can be either 0.4 mil thick or 0.5 mil thick. And that can then be popped into a graph. This is one thing that Excel is good at, is producing graphs and actually doing curve fitting. We can superimpose that onto the levels for high, medium and low wind as described by NZS 3604. From that, we can derive the maximum span for each of the roof configurations. And so, for example, for the 0.4 mil thick Metcom 7 sheet with fixings at 254 millimeters to match its ribs, has a maximum span under high wind load of 2.2 meters. Now, in this case, we're looking at steel battens, but we can also look at aluminium battens as well. And in most cases, they're the same, but occasionally, particularly on the extra high wind, we have to limit it because of the limitations of the fixings. And we repeat that process for all the different roof sheets, and then we become a summary, and we compile that summary into a nice big table for all the spans, for all the sheets, for all the different wind loads, low, medium, high, very high, and extra high. And then we can put a pretty picture in there. Again, something that Excel is quite good at is drawing pretty pictures. And this is a way of representing the different lengths of spans for the different families of roof sheets, going from Metcom through to E-span. So there's quite a big difference between the capacities of these different sheets. And we scroll down and find the same sort of thing for aluminium battens. Moving on, you then get the capacities, low, medium, high, wind for steel and aluminium battens for each of the sheets. So this one's for Metcom, then we go on to Kahoo, then so on, MC965. So that's your first starting point. So this is a roof on a roof, and your top layer is a standard roof sheet, and that can be the governing criteria. We then look at the panel, and this is an unusual panel, and open the Mathcad for that. We start with the fixings, and because you've got quite a complicated load path and many components, there are many calculations to do regarding the fixings. So we start with the fixings between the roof sheets and the battens. Then if we've got E-span, we're using a clip into aluminium battens. We've also got the fixings between the battens and the top skin of the SIP. And I should perhaps have told you that this SIP is a bit unusual in that it's got an aluminium skin at the top and it's got a steel skin at the bottom, which makes it asymmetric. We then look at the tension capacity of the PIR, and then the fixings through to the supporting purlin, and then perhaps through a batten to the supporting purlin. It's a slight difference between the two. So you'll have seen these calculations before. And this is a roof sheet to the batten, and we pop out with a design tension capacity based on the thickness of the material we're using. So as before, in this case, we've got a little matrix. It's a very small one-dimensional matrix or an array with two values. So our skin can either be 0.4 or 0.55 millimeters thick. So that gives you the two values here for the pullover capacity, 1.93 or 2.65. Okay, then we move on to the aluminium battens. And you'll see that the pullout of the aluminium dominates because we're using a 6060T6 aluminium, which is not a particularly strong aluminium. Then we look at the clips to the batten for the E-span sheets, and then we come out with a capacity of 1.12, and again the aluminium pullout dominates. Looking at the batten to the panel, first look at steel battens to the aluminium skin. And surprise, surprise, the aluminium pullout dominates. Sometimes we will use these in pairs, or perhaps to get up to the equivalent for a steel, we'll put them into sixes. Looking at different size screws, going from gauge 6 to gauge 14 screws, we end up with the capacity ranging from 0.18 kilonewtons to the 0.33 kilonewtons. Looking at the capacity of the fixings in aluminium battens and aluminium skin, we can get a similar calculation, and surprise, surprise, the aluminium dominates again. We're looking at the test results that we did. So 10 tests were done. Here's what the rig looked like. It's pulling out of a 10 gauge screw from a 0.9 millimeter aluminium. And so we can put this into a table, and that comes from the matrices and tables menu. just insert table. And a table is a special kind of matrix. It's two arrays. They have dimensions and they have units. And so each of those are a vector. So you've got two arrays of vectors. And because they're special vectors, you can do matrix mathematics on it. So you can count the number of rows, you can calculate the minimum in that particular vector, and find the standard deviation. And from that, get the coefficient of variance from 1170. So our nominal tensile strength is 680 newtons, and our capacity reduction factor is 0.5, giving us a tensile strength capacity of 0.34. So it's a bit higher than the figure we actually calculated. Looking at the PIR, again, there was some testing done on the strength of PIR in tension, and normally we will try to avoid tension in the PIR. So the test results are here. They just did 3 test results. Again, the coefficient of variation is quite small because the test results are all quite close together. And that gives us a nominal tensile capacity of 899 newtons. Because the contact area was 100 by 100, we end up with a tensile stress of 90 kPa. That's what we've used. And this is a look at the test rig of these PIR samples. Moving on, you've got the capacity of the panel to the purlin. Now remember, the top skin of this panel is actually aluminium, so that's likely to be the weakest link. Again, we're using self-tapping screws, 14 gauge, so we can pull those down. We have a pullover force of 0.48 kilonewtons. So again, aluminium is going to be the weak link in this situation. The pull out, well, that's pulled down from before, and that's not dominating there, but for various thickness, here is another table. So you've got thicknesses here from 1 millimeter to 1.8 millimeters with the ongoing tensile strength as 520 or 480, depending on the thickness. And we put that into an equation, and it's the same sort of equation that we've used before to calculate the pull out capacity from the sheet, but this time we're doing it on a vector. And the way we can do that is to use the matrix operator to vectorize that sum. Okay. Then we go on to battens to purlins, same sort of input and same sort of output. So in this case, your pull out capacity varies as it did above. So this is the steel batten. It's likely to be a top hat style section. And we're also doing an aluminium batten. And the aluminium batten looks like a channel. And we do the same sort of thing, but this time in aluminium, and we come out with a design capacity for the pull out. So that was the fixings. Moving on. So we're looking at the capacity of a composite panel, and it's asymmetric. It's got a different top skin to its bottom skin. So the top skin is aluminium, and it's a 0.9 millimeter thick aluminium. The bottom skin is the usual 0.59 millimeter thick grade 300 steel. And this is a bit of an experiment as to see what capacity you can get. The ongoing mentality that drove the idea of having an aluminium top skin was for corrosion and durability. Unfortunately, they selected quite a weak aluminium. This 5005 H35. It's a typical grade of aluminium used in sheeting. So the yield strength is only 130 MPa, and its ultimate tensile strength is 160. So we put our design parameters as we've done before for these panels, which you may have noticed in part 2 of this series of 5. But because it's asymmetric and it's composite, we need to use a transformed section. So here's a little diagram taken from a textbook that explains how a composite section works. So we pop in the modular ratio, which is simply the Young's modulus values for each of the two materials. So what I'm doing here is turning the steel into aluminium in effect. We need to find out the depth of the neutral axis because it's asymmetric. And by using the parallel axis theorem, we can calculate the second moment of area about the neutral axis. This gives you an elastic moment capacity depending on whether you're looking at the top or the bottom. And so this is going to be your governing because it's much smaller than the top in there. Moving on, we can look at wind pressures. And again, we've got our table with low, medium, high wind zones from NZS 3604, giving you wind speeds from 32 to 35. We can also pick out the difference between the ultimate wind speed and the serviceability wind speed from 1170 part 2. And from our table of speeds, we can get our wind pressures. So we're creating another little matrix here of an array of wind pressures in kPa based on the equation from 1170 part 2. We've taken the net pressure coefficient of 1.7, and that comes from the New Zealand metal roofing manufacturers. So this is quite conservative and is allowing for local winds, as you need to do on cladding. Quick look at the fixing loads. So what you're doing is taking the load in the fixing for each of the wind speeds. And if you look at it again under a continuous or a two-span continuous, the central support will have a significantly higher load in it because of that continuity. Quick look at the bending moments, shear forces and the deflections. And the reason I've done that is to show you that the capacity, the applied bending moment compared to the capacity, in this case it's the elastic capacity, is well within. In the worst case of the extra high wind load, we're at 47%. Same with shear force at 49 and deflection at 36%. So you've probably seen this equation before. That's for the flexural bending, and here we add the shear bending. So that was one sheet on one span. Let's take it a bit further. So now we do one thickness but multiple spans. Okay, same sort of input at the beginning. And now this time we have a range of spans, and we put it in as a one-dimensional matrix, so an array. So length is equal from 2.5 meters up to 7.5 meters. And from that, we can get our load span table for this particular panel. So it's a 100mm thick panel, and all we're doing there is taking the bending moment equation and turning it on its head to give you the loading that would cause the panel to fail in bending. And the loading in the fixings based on that is simply given by this equation that we've seen before. Take half the load and the spacing and multiply by the length. So we're looking at the spans here, and we come out with the fixing loads here. Spacing required to keep the fixing loads below the fixing capacity. Given that you've got a fixing capacity in each fixing of 1 kilonewtons, then it varies from the 198 millimeters up to 594 millimeters. Checking on shear, we're looking at the shear equation again turned on its head. From that, we get what load will cause the panel to fail in shear, and that's where we have an array. Now we need to transform our section again, which is what we've done before. We calculate the elastic moment capacity, in this case it's 3.11, and then we look at bending failure for that. So what we saw before with plastic bending failure, now we're looking at the elastic bending failure. So this is likely to be the limitation for an aluminium section. Then we look at mid-span deflection limitations. So we're going to limit our deflections under serviceability limit state to span over 150. So again, you'll recognize that equation as the flexural bending for a simply supported beam. And then we add on to that the shear deflection because of the PIR. And then we put it on its head and say, well, that's our limit, LP over 150. And then we vectorize it, and out pops a load span table going from 3.3 kPa all the way to 0.36 kPa, depending on your span. So that's for serviceability, but we want to turn those into ultimate limit state loads. So we use a USR, that's an ultimate to service ratio. In this case, it's the square of the wind speeds, because remember, wind pressure is proportional to the square of the wind speed, and it pops out as 1.479. This, of course, will vary depending on what region you've got. And now the new wind code has made it a little bit more complicated by having different ratios in different wind zones. For the purpose of this exercise, we'll just happily use the 1.479. So we pop out with a ultimate deflection limit at 4.87. So this is the load which will cause a 2.5 meter span panel to fail in deflection. So we can summarize spans by using the transpose sections. And the reason we are transposing them is so we can draw graphs from them. So for some reason, Mathcad only likes to draw proper plots and proper charts using vertical matrices. So we use the matrix function transpose, which you can find under the matrix table under T, and it turns your horizontal matrix into a vertical matrix. Simple. From that, we can produce our plots. So you've seen above, we've turned span into the transposition of LP, bending into the transposition of W under 100, and then again shear for WV 100. We then pop in a plot, and the plots are found on the plots menu, insert plot, and we put our traces in. So we've got 3 traces on the y-axis, bending, shear and deflection against the span. And in this case, we've chosen different colors for each. And oddly enough, deflection is now governing those loadings. So that was one thickness with many spans. So now let's add many thicknesses. So we go on to our composite panel, and we're looking at the same input parameters. We've got panel depths ranging from 50 millimeters to 200 millimeters, and we've now got spans ranging from 2.4 millimeters to 6 meters. There's a reason I've made the arrays the same size, because it makes it much easier to produce the graphs at the end. So it's the same procedure as we've had before, except because you've now got a matrix of numbers, you have to do these things in stages. So we start with bending, and again, you're looking at the familiar bending equation turned on its head. You see what the force is, and then you take out the span dependent part of that and put that separately. So if you think about WL squared upon 8, you're flipping it on its head, so you need the L squared underneath. So we create a variable called LM for each of those and multiply it by effectively the force. And we come out with this matrix, and I think it's a 7x7 matrix, giving the unit load for each thickness and each span, hence a load span table. Similarly, we do shear capacity checks. Here's your spans that we're considering, and I'm using my convention again. If I've declared a variable before, but I'm declaring it again, I just put it in grey. and the shear is going to be proportional to the length, so put 1 over the L to give you 1 array, and then we multiply that by what's effectively the shear force there to give you the loading which would cause the panel to fail in shear. A quick comparison, you don't really need to do this, but it's a nice to have. Take one from the other. So once you've got these matrices, you can do matrix mathematics on it, and all sorts of fun can be had. In this case, you can see that for any span bigger than 2.4 meters, then bending is going to be more dominant than the shear. But for under 2.4 meters, the shear will be dominating. Now we're looking at deflection checks, and to look at deflection checks, we have to look at the transform section. So you've seen that before, but this time we're getting bigger. We've got elastic moment capacities as before. Therefore, we redefine what the elastic bending failure limits are. So here is the load for each of these thicknesses at each of these spans. So for a 6 meter span for a 200 mil thick panel, it can take 1.39 kilopascals before it fails in bending. Okay, then we look at the deflection, and again we're limiting the deflection to span over 150. I'm looking at a simply supported span, and hey presto, out comes the load. And the keen-eyed will spot it. How on earth did you jump to that? What on earth is this DD? Well, all the complicated calculations have been hidden away in an area, so let's expose that. And yes, there they are. So Mathcad allows you to put in areas which you can hide, which allows you to do intermediate stages of your calculations as you need, as you go along. So most of these figures are fairly meaningless to the final value and fairly meaningless to anyone checking it, except if you really want to check it line by line. And because it's a matrix, you can't do everything all at once. And you rumble through all of these stages, you add them all together and come out with the deflection limits. So you want to ramp that up from a serviceability deflection limit to an ultimate deflection limit. And then you can create your DP thicknesses versus your spans for your ultimate limit state. Again, a little comparison, you don't have to do it. It just shows you that for 50 mil thick panels, your deflection is governing, and beyond that, your bending is governing. We can look at fixing loads. So if you set your fixings at 1 meter centers, you can get your kilonewtons per meter in effect. More realistically, your fixings are going to be at 200 mil centers. And that's what the fixing loads are, given the maximum bending load you're putting on. But if you've got a fixing capacity fixed at 2.7, for example, you can then calculate what your spacing is before your capacity of your fixing is exceeded. You can then repeat the procedure for your 2-span continuous, and then we're looking at wind pressures. So these are the fixing loads under each of the wind pressures, low, medium, high, and so forth. You can go into what's the deflection under unit load. This is a bit of a sidetrack, not entirely necessary. And then we can look at the bending capacity for each panel for each thickness, and then superimpose on that the high, very high, medium, and so on, the wind speeds across that. So this is for bending failure. We can do the same plot for shear failure, and then another plot for deflection failure. So these are the loads that would cause the panel to exceed deflection limits. And we can plot on the loadings for fixings at 1 meter spacing, fixings at 200 mil spacing, and so on. So that brings me to the end of the composite panel, but then there are other things to do. Just for a super bonus, and hopefully my battery will stand up to this, we're looking at creep. So a different project asked me to look at the snow loading and take snow loading as a long-term load. and take into account the creep in the PIR. And to do that, all we do is add these coefficients, creep coefficients. There's one for 2,000 hours for snow loading and one for 100,000 hours for dead loading. These you need to get from your manufacturer, and these vary enormously. And we've also got differences in the shear strength for long-term and short-term loading. Again, the 44 is quite conservative. So we pop those into our equation. We also take into account the mass of the panel, because we'll take it into the dead load. We add a service load, a mere 10 kilonewtons per square meter, to allow for lighting and cables and so on, minor light services. So we carry on, and we get the design shear capacity, the plastic section capacity, and the elastic section capacity. This is for a standard steel and steel composite section. So we've got steel skins top and bottom, so there's no need to do the transformation that we had before. We look at the bending capacity check, and that will pop out our bending load span table for bending failure. So from spans from 1.5 meter span through to 7.8 meter spans, and from panel thickness varying from 50 to 150. Okay, similarly, we can do it for shear. We turn that shear equation on its head, and then we produce the load that would cause the panel to fail in shear. And we do it twice because we've got a different value for the long-term shear capacity. So the long-term shear capacity is less than half of the short-term shear capacity. We look at deflection checks. So we've already calculated what our second moment of error is for the panel. And we look at the deflection limits. Now, what's hiding in my area is all the equations. So once again, we've set our limitation to span over 150, and we work that through. So this is for wind loading, no creep allowed. And we factor it up by the difference in the ratios between the wind speeds at serviceability and ultimate limit state. We then move on to deflection in snow. And again, let's open that hidden area. And we see very similar equations, but this time, here is our flexural deflection, and here is our shear deflection, but we've added on the creep coefficient for the 2,000 hours of creeping. So 3 months of snow you might sustain. And you work through the calculations again, lots and lots of tables of numbers, and we pop out with the serviceability limit state loading, and then we factor that up. This time we're using snow, so we want the difference in the factors for snow at ultimate versus service. So that pops out a remarkably similar figure of 1.47. So we multiply our serviceability limits by the USR, that's the ultimate to serviceability ratio for snow. And finally, we're looking at dead load. So again, we rerun that calculation. This time we're using the creep coefficient for 100,000 hours for dead loading. And on we go. So we use an ultimate service ratio of 1.2, because our dead load is nearly always combined with something else when we're looking at the dead load and deflection. And so we pop it out. Here is our limitations for the dead load. So that was the taking into account creep. We're looking at fixing loads. We have decided that our fixing spacing is going to be 250 millimeters. Our fixing capacity is 237 kilonewtons. So from that we can derive our limits on the fixings. So for simply supported fixings, it's only half the full load. So therefore we can get the load before fixing failure as 12.64. For the shorter spans, and then up to 2.43 for the longer spans. We can do the same for other variations other than simply supported. So continuous panel, in this case, a 4-span continuous panel, instead of being 0.5, we use a factor of 1.14. And so the allowable loading comes down considerably. So don't forget that your intermediate fixings are carrying at least twice as much load as your end fixings. We go on to comparisons. We don't really need this, but it's always nice to look at it. So for the shorter spans, the shear is dominating, and for the thinner panels, the deflection is going to be dominating throughout. So as we say, for spans below 3 meters, the shear dominates. For spans above 3 meters, bending dominates. And for 50 mil thick panels, the deflection governs. But for panels bigger than 100 mil, then your fixing load might govern. You might not get the whole fixing load available. Then we can produce charts, and these are slightly different to the plots, and you can find these not under the plot menu, but under the math menu, and you can insert chart from that menu. So I've inserted a chart and I've plotted bending 2 lots of shear, so short-term, long-term, the fixing load, the deflection, and the snow. And that is for a 50 millimeter panel. Now, how did I pick out the 50 millimeter panel? Well, again, we've got an area that's hidden lots of numbers, and you can see why when you look at all those numbers. We've got columns and columns of numbers. You will see nothing but columns of numbers by the end of this. So to make our plots actually do a nice line on our graphs, we need to transpose all of those parameters. So we go from our bending loads and we transpose it using the transpose functions from the matrices operator here. Similarly, we do it for shear, short term and long term, for deflection under wind load, deflection under snow load, deflection under dead load. And then we can also look at fixings and so forth. So from that, we get this set of arrays, and we end up with these transformed these transformed matrices. So instead of being for deep, they are now for wide. And so these are the different thicknesses of panels, and our rows are giving us our different spans. And from these matrices, you can pull out a particular row. So for a or a particular column. So for example, the bending load for a 50 millimeter panel is taken from the first row. So we take our transposed matrix and pick out the first column. Now in Mathcad, the first column by default is indexed as 0. So that then picks out that particular column. And similarly, we do it the first column for shear, long-term shear, and so on. And we do it for deflection as well. Repeat the process for a 75 mil panel, which is then the second column, a 100 mil panel, which is the third, and finally the 150 panel, which is the fourth column, although it's indexed as number 3. So from that, we open our chart, and hidden behind the chart is the components. So we can put in, under our math menu, a chart component. So you can put in an X expression and you can put in a Y expression. So our X expression is going to be the span. So for our Y components are going to be the load for bending failure, the load for shear failure, the load for shear failure in the long term, the load for the fastener failure, and then the load for deflection failure under wind and the deflection failure under snow. So that gives us many curves. And Mathcad allows you to reformat your chart. There's a lot more tools available compared to plots, and it's intended that charts are something that are published rather than your plots are something you do for your maths. The styles you can turn, you've got a limited amount of styles. You can do it as a single line, you can do it as a trace, or you can do it as columns. I think we still prefer the lines. The style of the chart, well, you can change the background color if you really wish, have a border, and so on. You can put a legend on, which we've put middle and right, so it's over here. And again, you can put a border on if you wish. You give the chart a title, so you type in the title there and tell it where to go, so it goes top center. There's a limited range, you can't just put it anywhere, but in this case it suits top center. So looking at the axes, and do you want check marks? Do you want grid lines? I've said yes, and we put our X grid lines on and give it a style of a dotted style. You give it a title, in this case span in meters. What's the setup? Now sometimes the default setup will work, which in this case it has. It started at 1.5 and gone through to 8 and give us 13 steps in between. If you want, you can rearrange that. Okay, so that was the X. Now let's look at the Y. Again, you have a setup. In this case, it's taken the default range. Now it's pulled out the raw numbers, and the raw numbers in pascals. If you want to display these in kilopascals, simply divide everything by 1,000. You can give it a title, so max pressure in pascals at ultimate limit state, and it tells you where to put it. Now, for each of the traces, I've got 6 traces, and I've given it a line. So my first one is red for bending, and you can tell what the line style is and whether it needs a cross or a tick. Similarly, the second one is green, and that's going to be for shear, and give it a particular line style. Longer term, give it a different thickness of line style, and so forth until you get your chart. So you can close that and it will update any changes you've made. And then you can hide the input by clicking on the minus sign. Then we move on, do the same thing again for our 75mm panel and our 100mm panel, our 150mm panel, and so on. So that was the raw data. Those are the loads for the panels in the different cases. What about finding the minimum? Now, unfortunately, you can't just use min as a function on a matrix because it will just pick out the minimum value and give you a single value. That's not what we want. We want the minimum value of each of the matrices at each point. So for each thickness and each span. So we want to end up with a similar matrix that we had before. So we do a little bit of programming. So first of all, we find out how many rows we've got. So our rows are using the length function for the matrix, and that gives you 4. So we've got 4 thicknesses. And then we look at the columns. How many spans are we looking at? Well, we're looking at 12 different spans. We initiate our matrix by giving it a 0 value. And then we go for all the rows and all the columns. We populate the values and we pop in the minimum of the load in bending, in long-term shear, and in deflection for snow load. And that pops out this matrix. However, perhaps we need to include the dead load, and the dead load is combined with the snow load with a factor of 1.2. So therefore we remove the dead load from the list above to find the downward maximum loading, and you'll notice that in some cases we have a negative value, which would imply that the panel can't even stand up to its own weight, which when you think about the span to depth ratios we're looking at is not really surprising. We do a similar thing for wind upload, and we take the minimum of the bending short-term shear this time rather than long-term, the short-term deflection, and then the fixing. And because the fixing is a one-dimensional matrix or an array, your row is therefore going to be row 0, the first. And it compares all 4 values and populates another table, W-min. Then we add the dead load, only using a 0.9 factor with that. So that increases slightly the amount of load you can put upwards on your panel. So we then draw charts, and we have charts for all of the thicknesses, in this case 50, 75, 100 and 150. We've put in a little table here so we can tell the difference between the two. That's just a manual addition, not particularly scientific. And then we do the wind upload that we're allowed. And again, for each of the thicknesses. The steps in the lines will correspond to the different failure mechanisms that you're looking at. So in some cases, these values will start to merge. And we add some notes. So these charts are to be used for roof wind loading and snow loading at ultimate limit state. Typical warning that we've got a minimum roof pitch of 3 degrees. And it's based on a simply supported single span panel. And our deflections have been limited to span over 150. We've made an allowance of 10 kilograms per square metre for light duty fixings, lights and so on. No other dead loads have been permitted. We're allowing for a live load, which is at 0.25, and a concentrated load, which is usually 1.1 kilonewtons, which usually is not the dominant load. Fixings are 14 gauge tack screws at each of the ribs. In our case, our ribs are at 250 centres. We're saying we've got a minimum purlin thickness of 2 millimeters. That way it's the panel that's failing rather than the purlin. But always check that your fixing is adequate. So that's the end of the normal panel design. Let's look further. Now I promised you some Excel. And now we export all of that data into Excel. This looks like programming, because it kind of is. We first declare a file name for our Excel spreadsheet that we're going to create. In this case, it's called single.xls because we're doing single spans. Then we need to populate that sheet with all of the parameters that we have derived. We start with the thickness. Now, one of the bad things about Excel, it doesn't understand vectors. It doesn't understand units. So we take our thickness, dp, the depth of the panel, and divide it by meters to give us the raw number, 50, 75, 100, and 150. So that's the raw number we're going to put in the Excel sheet. Similarly with spans, we've got to divide it by meters to turn it into just raw numbers. We give the thing a title, so this is for bending. So that title will go at the top of the load span table. Then we start exporting. So we use the right Excel function that you can get, and that comes under input output under Excel components. And there are right Excel functions which require a file path, which we've already described, the information you're putting in it, in this case the title, and where you're putting it, in this case the first sheet, and in the first cell, A1. And on we go. We put the thicknesses in A2, the spans in B2, and the actual spans, the numbers, into B3, and then the thicknesses into A4. We populate the data. Again, we strip out the units. So we're looking at the bending, which is WM. We divide it by kilopascals to get out the raw data. And then we do basic programming. We count the rows, which is the length of the matrix. And then we add the rows and turn it into a string by using the num to string function in Mathcad. And then we define what we call B cell by adding the initial B cell to the number of rows. So we take B and put it as B4. and we export that data. So export 6 is writing to Excel to that file path with that data. Data 1 is all of this, and it puts it in that cell, which is marked as B4. Okay, and then we do the same again for shear, deflection, fixings, download, upward load, and so on. So that will be a simple spreadsheet full of all these numbers. Okay, so that's exporting Excel. What about getting back again? Well, I've just punched it out and it's going to pull it back in again. So I can read Excel in this case. And so it will populate. So the simplest way of doing this, let's move to one side. You look under your Input Output tab in Mathcad. You insert an Excel component. Let's make it a bit bigger. And in the input, so there's an input here and output here, input expression, and then we read, and then we can browse, for example. And here is the file. You can choose which columns and which rows to take. It has automatically picked the ones that are populated at the moment, and even which sheets. And then you can insert that. In this case, it's put the full line in there, and it should populate that. Because it's probably busy, it won't. So I'll come back to one I prepared earlier. So it's populated the Excel sheet into the Mathcad. And we can edit it like an Excel sheet. If you double click on it, it opens up Excel. Let's make that a bit bigger. And you can format it like an Excel. So you see that one, you want it to be formatted like so. Then you can update your Excel and it should update it in here. You can also resize the column so it fits onto your page. And that is how you get your Excel into your Mathcad. And once you've got it in, you can start manipulating it. So that was the last of the Mathcad. For the references, again, look at the Metalcraft and Conqueror websites for some useful information. And the fixings are defined and calculated using NZS 1664 for aluminium and 4600 for cold formed steel. So that was the last of the seminars for 2023. We might come back with a seminar in 2024. All suggestions are welcome, and if you like that, leave a like, don't forget to subscribe to the channel and leave a comment. Any suggestions for future webinars will be welcome. So